The technique that we're going to use to graph general logarithms is not a difficult technique, but it does combine two moves that we haven't had a lot of practice with yet. The first one is the move that we used to graph the exponential. Rather than looking directly at the function we're given, we're going to look at the input and output of some base function, in this case the base log function. And then because we're graphing an inverse, instead of choosing input values, we're going to start by choosing output values. So our base function in this example is taking the log base 1/3. We're going to take the log base 1/3 of something. And we're going to use the outputs -2, -1, 0, 1, and 2. And the inputs that give us that are 1/3 to the -2, which is 9, 1/3 to the -1, which is 3, 1/3 to the 0, which is 1, 1/3 to the 1, which is 1/3, and 1/3 to the 2, which is 1/9. So those are the inputs that give us those outputs. Now we want to find out what x is required to give us these inputs. So let's see. When the input is 9, well, the input is 4 minus x. So 4 minus x is 9. That means negative x is 5. So x is -5. When x is -5, that gives us the input of 9. Okay, well, when 4 minus x is 3, you know, it's easier to guess that, right? 4 minus 1 is 3. X must be 1. When 4 minus x is 1, again, we can guess that pretty easily. That's when x is 3. If 4 minus x is 1/3, this is starting to be hard to guess again. We've got minus x is, this is a job for a calculator, minus 3 2/3. So x is 3 2/3. If 4 minus x is 1/9, then negative x is 3 8/9. Then minus x is minus 3 8/9. So x is 3 8/9. Okay, so that's how we find the x values that go with these y values. And then, how do we find the actual y values? Well, according to our function, our actual function is 2 times that log minus 3. So we're going to take these numbers times 2 minus 3. So 2 times -2 minus 3 is going to be -7. 2 times -1 minus 3, that's going to be -5. 2 times 0 minus 3, well, that's going to be -3. Notice we seem to be counting up by 2's. And that makes a certain amount of sense because our outputs are counting up by 1 And then what we're doing is linear. So if our outputs are going up by 1, we expect our y's to be going up by some constant amount. And in this case, it is 2. 2 times 1 minus 3 is -1, and 2 times 2 minus 3 is 1. So -1 and then 1, counting up by 2's. Okay, so let's see what our graph is going to look like. Our y values go from -7 up to 1, and our x values go from -5 up to, well, something close to 4. So it looks like we want our x-axis to be close to the top of our graph, but not all the way to the top. And our y-axis to be kind of down the middle, right, between -5 and +4. Let's see what we have room to do with that. So it looks like we just barely have room to draw that. -7 is going to be all the way down at the bottom of our graph, but that's okay. So let's look at the points that we have and see what it looks like when we actually plot them. -5, -7, that's going to be all the way down here. And then we've got 1, -5, all the way over here, 3, -3, and then we've got the kind of harder to plot ones. We've got 3 2/3, -1. So 3 2/3, split this up into 3, and take 2 of them, right, 3 2/3, and then 3 8/9 is going to be real close to 0. It looks like our values then are getting really close to 4. Right, as we get closer and closer up here, we're subtracting something closer and closer to 4 from 4 in order to get some small number. Looks like our vertical asymptote is going to be at x equals 4. And we're approaching that as we go upward. And then we'll just fill in kind of a smooth curve. And our graph is going to look something like that. So we've got that upside down log function the way that we did with bases less than 1. And it looks like it's also to the left of the asymptote, not to the right. Interesting. How do we talk about this? Well, the place where we have our asymptote, this is at x equals 4, the argument of our log was 4 minus x. This is where 4 minus x equals 0. The vertical asymptote happens where the argument of the log equals 0. And then what made this be to the left of the asymptote? Right? Well, what put us to the left of the asymptote is that we needed a negative value of x to get a large value of the input. And the reason that that happened is that we were subtracting the x in our argument, right? This move right here is what made us flip that x around. So if the coefficient of x in the argument is negative, that's when we'll have this backward graph. That's when we'll have this graph that's to the left of the asymptote. And then typically our nice key points, if we had a really good idea of what this was going to look like, we could potentially have drawn this graph using just those 2 points. Right? We knew if we knew in advance where the asymptote was, and we know the general shape real well, those 2 points are enough to give us where the graph is and how big it is. So how would we find those 2 points in general? Well, we start with outputs of -1, 0, and 1, which correspond to inputs of, well, if our output is -1, our input must have been 1 over the base. If our output is 0, our input must have been 1. And if our output is 1, then our input must have just been the base. And this will usually give us 2 nice points that we can use to draw a graph. Not always. Sometimes just all the numbers that turn up happen to be fractions and we roll with it. But often, choosing the outputs -1, 0, and 1 will give us 2 nice points and 1 unpleasant point that we don't need to use if we don't want to.